Hello everyone, this is the solution video to homework 3. Now we had two questions here. Um, One of them was the question where we have a step response, which is the step response of a closed loop, and we were trying to find the transfer function and then find the open loop transfer function, refine our choices, and calculate the parameters because it is known that the open loop system is a mass spring damper system. So let's dive in. Now, first of all, we have this plot here, and what we have to do is basically take some measurements. Now, first of all, we have to observe that we have a grid here, and if this is 0.6, if this is 0.8, we have basically some steps here. This corresponds to 0.7, 0.75, 0.65. If we draw the line, we can see that this line here is 0.65 and a little bit more than that. So let's choose the steady state value approximately 0.66. So 0.65, but I approximated it to 0.66. Now that's one measurement that we took from here. The other one here is basically the peak value here, because when I have the steady state value and the peak value, what I can do is I can calculate the overshoot, and that can give me zeta, for example. Here I'm going to take the peak value as 1 because it is slightly more than that, but you can take whatever you want. But I guess I'm going to take the peak value exactly equal to 1 because I need to refine it anyway, so that wouldn't be a big deal. Now we have the peak value and the steady state values here, so the overshoot should be y peak minus the steady state value divided by the steady state value. So I'm not going to multiply it with 100 because we need this as a floating point number than a percentage because we use that for the calculation of zeta. Now I am also interested in the steady state value times 1.02 or 0.98 because these are the upper and lower bounds of the settling time band that we should enter, and that time instance where this happens is going to be my settling time. So let me display the values here. I didn't define YSS, so it's going to crash. Let us run Q1. So, well, we are going to be interested in 0.67 or 0.64. So this was basically 0.66, and when I come here, I can see that here somewhere I am entering the band here, approximately here, I guess. We're entering it from the top, from the upper bound here. So let's see. If this is 10, 11, 12, 13, 14, 15. So this is 14. It's a little bit more than 14, but let's take it 14. Let's take this point as the entrance point because it's somewhere here. So let's take the settling time 14. TS equals 14 seconds here. So once we have that, what we can do is we can go ahead and calculate the zeta and omega n values. So let's start with zeta here. And the zeta value is going to be the log of overshoot divided by the square root of pi squared plus log overshoot squared. So, and of course the natural frequency then would be 4 divided by Ts times zeta here. So let's see what zeta and omega n seems to be. So 0.2 and 1.38 seem to be the values that we are looking for. So now if we know what the settling time and overshoot values are, and if we have converted them into zeta and omega n. What we can do is we can write a second order transfer function. So let's call it experimental closed loop, TS. And it would be a TF transfer function. Ideally, I'd pick 1, 2 times zeta times omega n, and then omega n squared. So that would be ideally what we would pick here. But of course, we have a steady state value, and we have to add that to this system so that the DC gain is basically the gain that we need. Therefore, we will add YSS times omega n squared here, so that in the steady state we will have the steady state value 0.66. So let's see how the closed loop looks like now. Now, what we can do is we can also generate the step response here in order to visually compare if it's working, if it's looking good or not. So I'm going to choose grid miner here, and let's basically calculate y comma t, tsexp, and plot t comma y with increased line width, x label, time, title, closed loop, step response. So it seems like we are not able to see the grid that we have here. So what we can do is we can adjust that. So let's have x1 minor grid color. Let's convert it into black. Minor grid line style equals solid, and ax1 minor grid alpha equals 1. So let's see if it makes the change here. Yeah, at least we have that. Of course, our simulation was a 30-second simulation, which is not the case here. So let's increase the final time here to 30. Now we have 30 here, but our Y limit doesn't seem to be the same. That seems to be different here. Yeah. So what we can do, we can just change the Y limit here to 0 and 1.2, x1. Maybe that helps a little bit more. There we go. Now if I open this up and put this here, we can basically see some resemblance here. So yeah, let's zoom in a little bit. Seems like it, I'd say. The peak value needs a little bit to be a little bit higher, somewhere here and 14. Of course, there are some differences, but this is based on our values here. So we kind of have completed the first part where we get the closed loop transfer function, which seems to be equal to this one here. So let's go one step further. We know that we have a controller, and we know that our closed loop looks like this. So what we can do is we can just take this controller to and GS and calculate basically. So let me just put in here part 1. So we can just calculate the open loop. So we have KP equals 2, and ideally this would look like 2 times GS, or KP times GS, divided by 1 plus KP times GS is going to be equal to TS exp. So if I multiply this with this here, and even expand it, so I would get this here. What I want to do is I want to work out what GS is going to be in terms of the remaining transfer functions. So we have a common term GS here. So it would look like the following. So in the parentheses here, let's get rid of GS. So it means that I'm going to divide into this one here. Of course, I can also factor out KP here, and it would mean that I take this one here and divide it into KP. So I can directly calculate this with using basically the feedback command. Here we have tsexp and a -1 here, so that it will calculate this. If you think about it, this is the feedback command for the positive feedback loop. So that's the reason why I provide another negative here. And if I divide this into KP, this would be GSexp here. So let me comment this out here. So let's see. So there we go. Now, so let me zoom in a little bit to see both of them. So the closed loop looks like this, but if we use the controller, this KP2 here, then we get basically the open loop that looks like this. So 2 times GSX divided by 1 plus 2 times GSX, the step response of that should give us this result here. So basically, we have a guess for our transfer function GS at the moment. So now what we have to do now is to, because the third task here is to refine our GS to match the closed loop step response with a given step response in figure 1. So we have to refine our choice, and let's try to look at it. So how can we adjust basically our choices here? So now the open loop transfer function that we have acquired is in a form where we have a coefficient in the numerator. But usually if we're talking about a mass spring damper system, what we have is we have ms squared plus b times s plus k as the transfer function of such systems. So what we can do in terms of adjustment is the following. We can get the numerator dot numerator and also the denominator. Like this. And then we can look at the denominator and divide it into the value of the numerator. I'm going to type in end, and the reason for that is that the numerator vector will have zeros for s square and the s terms, and the constant term will be the last one, so therefore I'm picking the last one here to get basically the coefficients that I'm going to be interested in. So basically what I'm trying to do is I'm trying to actually, I'm kind of jumping to the next one here, where I calculate the mass damper and spring constants here, but not entirely, because I have now these coefficients. So the first one would be basically the mass of the system, the damping coefficient, and the spring constant. So what I'm then going to look at is basically I'm going to define GS again, but now I'm going to take the values from the denominator here. So M approx is going to be the denominator, the first one here, and then B approx would be denominator 2, and then K approx is going to be denominator 3, and I'm going to define my mass damper spring system, M approx, B approx, and K approx, like this. So then we will have basically our closed loop here. We know that Kp times Gs, comma 1 is going to be the closed loop that we're interested in. So we still have this one here. So maybe we can take this part here. If you look at Ts, so let's pick a red color here, and AX1 here. So there we go. So now we basically have our transfer functions here. So GS, and what we can basically do is we can basically change the settling time a little bit to try to match the value here. So that would correspond to the following. We have basically, where's our settling time? Here. So what happens if we, for example, add a little bit to the basically settling time, we get again this result here. Maybe we can tweak the peak value a little bit, maybe increase it a little bit. Which seems to be okay in this case. So what we can again do is to look at the step info of the resulting settling time that we have at hand to try to match them. So we can see it's 14.99 and the overshoot is 50/95. So let's display ours first. So display the settling time. The TS value here, and overshoot is going to be OS seems like times 100 is necessary at this point. And let's suppress all the output that we have here, for example this one here, and then maybe also this one here. So we might be interested in GS, but after that. So let's run this. We can see that we're almost matching the values here. The settling time is a little bit off. So we can see that we have almost 53 here. The overshoot is almost equal here. The settling time value seems to be 15. We're 15.4. So maybe we should decrease it a little bit. So maybe 1.05. Let's run it again. So the tuning is basically here. We're kind of closing the loop in some sense because we're trying to match the overshoot and these values almost exactly to get basically the actual values here. So we're going to toy around with stuff here. So we have almost the overshoot again, but settling time keeps failing here. What happens if we increase, or let's decrease it maybe. Let's take 90%. Of course, we could write a little for loop here that kind of matches these here. But yeah. We have still some issues here, I guess. So maybe let's increase it. Let's try this again. So let's increase it a little bit more. So it's not really helping. So maybe we should try 13. 11. What happens if I decrease it even further? Well, that doesn't help. And is also not correct. So yeah. We're kind of stuck here. But I also don't really want to complicate it too much. So let's try 15.5, 13.7, 51.3. Maybe slightly more. Yeah. Well. So we can actually go on like this. But it doesn't really affect the coefficients that much here. We can see that we have a certain certain values here, and as I've said before, we can just make a slide table that wiggles around the settling time a little, and maybe also the overshoot, and tries to minimize the difference between the resulting step info from TS and the values that we have here. So it can try to match it, but it's not really that important. A slight wiggle and slight self-adjustment here is sufficient actually. And here we can also see that we have certain values. And let me show you what happens if I round them. So conclusion part. What happens if I take the values, instead of being approximate, equal to 1.967, I'm going to take it as 2. The coefficient is equal to 1, and this is also equal to 1. So what happens if I take this and use the feedback and plot this and look at the step info here? So let's assign it another color, blue. And let's see what we get here. So as you can see, there's slight variation where we did approximate it pretty much as good as possible. So it seems like it was 14 or 13.99 here. But then again, we have some issues with the accuracy of our formula. 13.99 if I take this instead of 14. I should also remember that the coefficient here is something like 3.91 or 3.8, depending on the accuracy that you're looking for. So let me just run it back. And then you would see there are some differences. It increases the difference between that, and it is way off. So I'm not going to go into changing these values. So let's leave it there. But you can see that if we are matching it, we're matching it with the coefficients 2, 1, 1. These are the nominal coefficients or parameters, but yeah, you can see that it's quite hard to come up with the actual value of the system because a slight measurement error causes us some issues. We can approximate the overshoot quite well, by the way, which is important to note because we kind of match that because yeah, we are looking for the peak value here, so it's not really that difficult to mess it up. But settling time is a whole different story because we can mess up stuff there. The settling time formula accuracy comes into play, and various differences end up being quite important here. So if I am going to wrap it up, let me just show you the questions here. So in the first part, we've directly taken some measurements. We knew that the measurements were not exactly correct because we're kind of eyeballing it here. Then we have basically used the settling time and overshoot. You could have also opted for something else to come up with the 10 omega n values. Then we proposed a supposed closed loop transfer function. We used the relation with the controller and the unit feedback loop and the open loop in order to end up in the closed loop transfer function that we've calculated. Now here we kind of skip this part for once. We try to calculate the parameters. We then plugged it in back. It's kind of a feedback loop in itself during the verification step. We have calculated the parameters here and used those used those parameters and defined the open loop and tried to match the step info that we have chosen and the resulting one to refine our choices here. So why is this needed? Well, this is kind of debatable in this case because yeah, for real-world applications, refining is maybe a good idea, but doesn't really help that much because no system at all can be directly calculated with these parameters. The nominal parameters will change with various conditions, with various parameters, and there are modeling errors. It is not going to be a linear transfer function after all, so it doesn't really matter to try to match it as well as possible. When you have noise, when you have measurement noise, measurements become even less reliable. So for real-world application, I would argue that this is not really that necessary. It still doesn't mean that you shouldn't refine your measurements. But yeah, at least we are trying to get rid of the errors caused by eyeballing it or by reading the measurements, but there will be noises and stuff, so it will have differences here. This is under if we would have been talking about ideal or mathematical reverse engineering as we did here, then it becomes important because we are just talking about theoretical stuff at this point. So in the real world, not really that helpful because measurements are not reliable, but ideally of course, it helps. We are trying to readjust ourselves. So then we have another question, question 2. In question 2, we have again step responses and again of closed loop transfer functions. But the case here is a bit different. We're just looking for a third order transfer function. We know that there are 3 poles in the transfer function. We know that there's no zero, and we know that the closed loop is calculated using a p-type controller, and we can see that the values are also given. For the upper plot here, we have the p-type controller 4.5. For the lower one, we have -8. So this is a technical question at this point, because if you know what to seek for, then it's kind of easy. But if you don't, then this kind of can become a headache at this point. So again, for the first step, what we need is we need some measurements. And this time around, what we are going to measure is basically, so let me get rid of this, let me clear the console. So this time we have a sinusoidal wave. And what we need to measure at this point is basically the period or the frequency of this, because sinusoidal waves make sense if we have a period here. So I'm going to take this lower part here and this lower part, and I'm going to try to measure the difference here so that I get just the period here. So this one here is around 3, but 3.2 would be this one here, 0.4, 0.6, 0.8, and then 4. So it's kind of in the middle somewhere, but I'm going to just choose 3.1 for this here. And here we're almost at 6 here. So I'm also going to choose it a little bit less than that, so 5.9 seems to be the choice here. So let me write them down. So the period is 5.9 minus 3.1. So if I know that this is the period here, I can take the inverse to come up with the frequency. And furthermore, if I know that this is the frequency, I can use 2 pi f in order to calculate an omega value here. And there's another conclusion that I can draw from this here. If you think about a certain third order system, when we calculate the stability margins of a third order system, what we most of the time end up in is a j omega crossing with a certain omega value and an origin crossing. And these two cases, if we have a j omega crossing and if we have a j0 crossing for certain p-type controllers, and this is mostly for -k, what we will end up in is that one of the roots for the j omega crossing would look like this, or a set of roots would be looking like this. So s plus j omega and s minus j omega for that k value, specific k value, which translates into s squared plus omega squared. So this is kind of a portion that we would get. On the other hand, if we have a j0 crossing, this would be basically one of the roots here. Since this is 0 plus j0, we would end up seeing an s term here. So if we apply step to a transfer function that has s squared plus omega squared in it, and a certain third pole, let's assume, what we would see is we would see this topper step response. And the reason for that is that the inverse Laplace of this whole thing here, 1 divided by, or omega squared p divided by, this whole thing here in the denominator would give us some sinusoidal terms and some exponential terms, but the sinusoidal term will be important because it is a constant sinusoidal wave here. So basically, this corresponds to a j omega crossing, and therefore we get a sinusoidal output. Whereas this one here, the lower plot here, has an integrator in it because it's a J0, an origin crossing, and therefore we get an S term, and if we have S term and apply step, we basically get this response here. And the nice thing about this question is that we know what values we have. For example, 4.5 is going to be this value here, and k is going to be -8. So we have an idea about this. So that's quite nice to have. So if I'm going to define my polynomial, because I'm interested in the polynomial here, if I'm going to define it, I would like to use this definition here. So let us define times s, and then PCS s squared plus omega squared times another pole that we don't know. But this is for a certain k value. And if you remember, ns divided by ds is the open loop, and if we have a p-type controller, then PCS becomes basically k times ns plus ds, like this. So we, for the moment, assume that this is basically 1. So we have k plus ds here. So it means that we're adding k and ds here. If I want to get ds on its own, I need to basically subtract k. So if this is PCS, I would define basically the actual system denominator as minus k, because I need to add k in order to end up in the j omega crossing. So now if we have a different gain value, by the way, I know what k is. So k is 4.5. So if I subtract 4.5, I know that this should be it. So let me also define sims p real. We don't know what that is, but we know that this is basically the experimental data that we've taken here. So let me just show you what it looks like if I write it down. Of course, this was just to hint ourselves. Let me get rid of that. There we go. Now, of course, let me just expand it in order to see, or in order to visualize it a little bit better. And maybe collect also the S terms so it seems to be organized. So there we go. Now we can see we have s cubed plus ps squared plus 5.036 times s plus 5.036p minus 4.5. So, and you can see if I have plus k, if I add plus 4.5, this term vanishes, and I can basically end up factoring this one out. So this would be s plus p, and then there's also s plus p. So if we factor out s plus p here, we would get s squared plus 5.036, which is going to be our j omega crossing. So what about the negative coefficient here? Or basically the origin crossing. So now if I'm going to add the value here, so basically I'm going to add the value minus 8 here, so that if I add minus 8 or if I subtract 8, I should end up in an S term here. So let me just repeat that here. So what happens if I have -8 here? It would end up being this one here. But I know that this polynomial, since I have used k equals -8, I know that s is going to be one of its roots. So what I can do is I can substitute s equals 0 here. These terms will vanish, and I'll get the value for p. So let me quickly do that. So let's substitute into PCS s equals 0 and solve that in order to get the p-value here. Let's also convert it into double in order to calculate the value of p. We can see that it is 2.4824. So this is basically our p-value here. And if I substitute it back in, subs PCS p-val, then you can see this is approximately equal to 0. I have an s term here and then the remaining part. So it seems like it is working. So now what we can do is we can basically substitute the p-value into this one here, and we should get basically the polynomial that we have here. So when we have that, what we can do is we can just basically define our transfer function now. TF1, seems like 1, 2.482, and then 5.036, and then 8. Seems like it. So let's basically look at the root locus here. First of all, let's have it side by side, the positive one and the negative one, and we'll see if it's kind of working or not. So our locus of GS, and then maybe plot the omega value here. So well, we can actually PZ map, so poles, no zeros, PZ map, and then feedback, and 4.5 times GS, 1. So I'm basically looking at the 4.5 value, so this case here. So I need the poles, so I'm going to plot the real part of poles versus the imaginary part. And then also maybe a line width of 2. And we might also want to plot the measurements that we did. So it will going to be 0, exp, and then maybe a red, is that a red circle maybe? And then also a line width of 2. So let me first of all run this. Takes quite some time for some reason. Okay. There we go. Now we can see that we have basically a gain value that we've used here. It seems like we're pretty much good, oh, almost there in terms of approximating it, but this is expected due to the case that was in question 1. So we need to maybe refine our choices a little bit in order to match them to get them on top of each other. So let me just repeat this for the second part here. The negative root locus. Therefore, I'm going to choose -8, -8, and we will have the poles, and we were looking for the origin crossing basically, so it's not even important in this case, but yeah. So now we can see that this was what I was talking about. Originally we have some poles here, but if we choose a point with k equals 4.5, then we have a j omega crossing because we have a sinusoidal step response. And if we add a negative gain to it, we kind of go back a little bit. So this one goes to the right here, and we have an origin crossing. Therefore, we get basically this result here. But since we have already a complex conjugate pair, that complex conjugate pair is going to be still there. But since we have an origin crossing, this will give us a ramp response, and due to the negative value, it was going down. So what we still can do is we can still create the subplot here, and then look for the step response of feedback of 4.5 times ts, 1, and then plot them, t, y. So it's blue, so we can choose blue. Of course, X label is going to be time. Let's have a title of k equals 4.5. And then maybe the part where we had this here. So let's add that too. Here we go. So 10 seconds of simulation time. Let's also choose that. Yeah, and let's repeat this for 2 here. This is going to be -8. It will be AX2. And then -8. Yeah, and I'm going to change this to 1 to get the same effect here. Of course, we didn't choose great minor here, I guess. So let's run it again. There we go. Now we've basically generated the same plot here as this one here. So yeah, this is basically it. We might, of course, change our choices a little bit, but you can see it kind of holds. So yeah, we kind of reverse engineered our way here. And it was basically important to recognize that this would be a j omega crossing because it's a special system, it's a third order system. And if you look at the root locus, we have basically crossings here and these are basically stability bounds. And if you can recognize that, and if you can handle that information and convert it into the steps that we have gone through, then you can end up with the solution here. Of course, it's not entirely exact here. As you can see, the crossing is a little bit probably off. Now this wouldn't seem like off, but I guess the one on the left is a little bit off, and it's understandable because we're still measuring stuff here. And this is a slight difference here, so it's not really that important, so we can live with that. So basically, these steps can be reported. I, of course, didn't create a report. I had just the design of the questions here, but hope that this was a fun exercise for you. And yeah, hope that this video was helpful. See you in the next videos.